Welcome back students to the video lecture series. I am Adil Mansoori from Civil Engineering Department of LG Institute of Engineering and Technology. The first topic for today's discussion is minimum and maximum velocities in a sewer. Okay, so we all know that the sewage always contains suspended particles. Okay, they have the sewage always contains suspended particles. The flow inside the sewer is usually under the gravity, right? Because we don't need an extra energy that is supplied by the pump for the flow of sewage, right? So the sewer lines are laid such that a particular gradient is maintained and the flow is under the gravity. Okay, so once again, the first thing is that the sewage always contains suspended particles and the flow is under gravity. Okay, now the minimum velocity which doesn't allow suspended particles to settle is called non-silting velocity. Okay, so the minimum velocity which doesn't allow any suspended particles to settle down in the sewer at the bottom is known as the non-silting velocity. Okay, now very high velocity will cause scurrying of sewer material. Okay, because if the flow of the sewage will be high, then what will happen is that the flow will try to scur the bed of the sewer, right? As a result, the sewer will need maintenance. Okay, so the maximum velocity permitted without scurrying of the maximum velocity permitted without scurrying of sewer material is called non-scurrying velocity. Okay, so minimum velocity is like so the first thing is that the velocity of a flow should not be such that it will allow the particle to settle at the bottom, and the velocity of sewage should not be that much more that it will scur away the sewer material, right? So the maximum velocity permitted was the maximum velocity permitted without scurrying of sewer material is known as the non-scurrying velocity, right? And the velocity in sewer therefore should be non-scurrying and non-silting, right? Now sewers are designed for full half condition, that is, now sewers are designed for half full condition, 3/4 condition or 2/3 full condition, right? Because the extra space acts as a factor of safety for two reasons. First is infiltration, that is the external water will come inside the sewer, right? That is known as the infiltration. And the second one is the unforeseen increase in population, right? Okay, unforeseen. And next is unforeseen increase in the population, that is the unpredicted increase in the population, right? So these are the two conditions that we are considering, and we design current flow as half full or 3/4 or the 2/3 of the full condition. Understood? So let us now move towards the Schill's expression for self-cleansing velocity. Okay, so this yellow triangle determines the land, that is the surface of the earth. Now we are placing a sewer at an angle theta with the horizontal. Okay, there is a particle ABCD at the bottom of the sewer. Okay, so consider there is a particle ABCD at the bottom of the sewer. So consider that there is a particle ABCD at the bottom of the sewer. Okay, now let the length of this particle be 1 unit, let width of this particle be 1 unit. I'll write over here length 1 unit and width 1 unit. Okay, and T is the thickness of the particle. Okay, now this arrow will indicate that this is the weight of the particle which is always acting in the vertically downward direction. Okay, now since this angle is theta, this angle will also be theta. Agree? Because there will be a component which will be perpendicular to the sewer. Okay, so since this angle is theta, this component will be W cos theta, and this will be the perpendicular component to the W cos theta will be known as W sin theta. Understood? Tau is the drag force that is acting on the particle because of the flow of water. Okay, and the bottom of the surface, or the bottom surface of the sewer, and the bottom surface of the sewer will try to not allow the particle to flow. So this force is known as the resisting force. That is, R will be always equals to W sin theta. Understood? Right? So let us now go for the derivation. Right? So we already have considered that length is 1 unit, right, and width is 1 unit. Right, now thickness is T and thickness is T. Right, so what will be the weight of the particle? Weight of particle A, B, C, D will be equals to volume into density. Right, now since the sewage is flowing inside the sewer, right, it will contain solid as well as water, right, and particle that we have considered is at the bottom of the sewer, right. It means that the particle will be submerged in the water. Understood? So this density will be the submerged density. Agree? Right? So this will be, therefore W will be equals to, volume will be L into B into T, that is 1 unit into 1 unit into T, into density, that is submerged density, I'll write as gamma submerged. Okay, right? So this will be equals to T into gamma sub. Okay, but we know that gamma sub, that is gamma submerged, that is submerged density, is always equals to G minus 1 upon 1 plus E into gamma W, where G is specific gravity, right, E is void ratio, and gamma W is unit weight of water. Right, students? Now we know that N is porosity, right, and the formula for porosity is E upon 1 plus E, right. Therefore Therefore 1 minus N will be equals to 1 minus E upon 1 plus E. Therefore 1 minus N will be equals to 1 upon 1 plus E, right? So can we write from here, you keep this formula in mind and this formula in mind, okay? So therefore W will be equals to, we know that it is T into gamma submerged, right, that will be equals to T into G minus 1 into gamma W upon 1 plus E, right, students? but we have known that 1 upon 1 plus E is 1 upon 1 plus E is 1 minus N, right? So this will be equals to G minus 1 into 1 minus N. In place of 1 upon 1 plus E, I am writing 1 minus N into gamma W as it is and into T. Name this equation as number 1, right? Now, when the sediment is just on the point of sliding, right? So when the sediment which is at the bottom of the sewer is just about to slide, at that point of time drag force is always equals to the resisting force, right? It is from the fundamental of the friction. Okay, so we know that R is equals to W sine theta, right? And tau is the resisting force, right? So therefore tau will be equals to, in place of W I am writing this equation, so this will be equals to G minus 1 minus N to gamma W into T into sine theta, right? Name this equation as number 2. Okay, again drag force tau, that is the drag force, is exerted by water, right? It is exerted by water. So can I write that tau is equals to gamma W into R into S, where R is hydraulic mean depth. Okay, so this is the formula of drag force, right? That is tau is equals to gamma W R into S, where R is hydraulic mean depth and S is bed slope. Okay, so now what I'll do is I'll name this equation number 3, and now what we are going to do is equating equation number 2 and 3, right? So what is equation number 2? Tau equals to G minus 1 into 1 minus N into gamma W into T into sine theta, and tau equals to gamma W R into S, right? So let us equate both of them. Therefore G minus 1 minus N gamma W T into sine theta, that will be equals to gamma W R into S. Okay, so what will happen is gamma W will get cancelled out, right? Therefore, and substituting 1 minus N and sine theta as beta dash, as beta. Okay, therefore substituting 1 minus N into sine theta, that is constant, equals to beta, right? Therefore G minus 1 into beta into T, that will be equals to R into S, right? Therefore bed slope S will be equals to beta by R G minus 1 into T. Okay, so this is the equation of bed slope. Okay, now if we consider ABCD particle as sediment of circular shape, then we can replace T by diameter D dash, right? Therefore S will be equals to beta by R G minus 1 into D dash, right? So if the particle is cuboidal particle, right, then the bed slope can be found out with this equation, and if the particle is spherical particle, then you can find out bed slope with this equation. Okay. Now from Chase's formula, can you remember, students? We discussed in the last video about the Chase's formula. Settling velocity equation is V equals to C under root of R into S, right? Therefore V equals to C under root R into under root of, in place of S, I'll write this equation, this one, okay, the bottom one. So that will be equals to beta upon R into G minus 1 into D dash. So under root R in the numerator and denominator will cancel out. So this will be C into beta under root beta G minus 1 into D dash. Okay, so this is the equation of settling velocity, right? Okay, now from Darcy's formula, what is head loss? We have been studying this equation from since long time. 4FLV square upon 2GD, right? Therefore head loss by L, that is HL by L, will be equals to, instead of 4F, I'll write F dash into V square upon 2GD, right? And head loss by L is bed slope, right? We have already studied this in our second module, that was for collection and estimation, right? So F dash will be equals to F dash V square upon 2GD, right? And therefore making formula subject to the formula V will be equals to under root 2GDS upon F dash, right? Name this equation number 5. Now again from Chase's formula or Chase's equation, V is equals to C under root RS, right? So C under root RS will be equals to 2GDS upon F dash from this equation here, right? One equation we have taken is the first one here, and the second one we have taken this equation. We are equating these two equations, right? So therefore C will be equals to, SS will get cancelled, under root S will get cancelled out, right? So what will remain is R is hydraulic mean depth, which is always A by P, and for circular section it is pi by 4 d square upon pi d, and that will be equals to d by 4, right? Always. So here, since we have considered d, small d, we will write as small d, that will be equals to 2gd upon f dash, and therefore we got constant c equals to under root of 8g upon f dash, right students? So we got only the constant c, right? Now where is the equation? Here, this one, fourth equation, right? So place value of constant c in this equation, right? So I'll write over here, putting value of c in equation number 4, we get settling velocity as under root of 8g into beta into d dash into g minus 1 upon f dash, and this equation number 6 is known as self-cleansing velocity. That is the equation of self-cleansing velocity. Understood, students? So I hope you must have got the clear idea of this derivation.